Swayam Prabha. Digital India. Educated India.
Today's lecture, in today's session, we will continue our discussion on wave drag. As you have seen in the last class, we talked about wave drag, and we were focusing primarily, well, we were not focusing, but we brought into the discussion wave drag on vehicles that are flying supersonic. So if you remember, we said that when the vehicle as a whole is flying supersonic, of course, the flow as it goes over the body of the aircraft, depending on the way the deflections occur, you can have oblique shock waves, you can have expansion waves. These will influence the distribution of pressure on the surface of these, say, on the surface of the wing of the supersonic aircraft. And then from the pressure distribution, due to the wave distribution, you can get the force distribution. And from the distributed force, you can get the resultant force. You can resolve the resultant force normal to the relative to get the lift. You can resolve it along the direction of the relative wind to get the drag. In today's lecture, we will focus on subsonic vehicles. I mean, we will get into the aspect of subsonic vehicles and see that when these subsonic vehicles, unlike the supersonic vehicles, when subsonic vehicles fly at speeds close to the speed of sound, so you can think of it as the transonic range. We will see other considerations like the critical Mach number, the drag divergence Mach number, etc., that will show up. So essentially, in today's lecture, we will focus on subsonic vehicles. So vehicles that are not flying supersonic. Okay, the vehicles are flying subsonic, less than Mach 1, but they are flying close enough to Mach 1 so that there are pockets of flow on the wing surface or etc., where you locally achieve supersonic flow. Okay, so while the vehicle as a whole is flying subsonic, it is at the high end of that subsonic range, almost close to Mach 1, so that local accelerations, when your vehicle is flying, there are flow accelerates in different portions of the wing, etc. So if it is flying close enough to Mach 1, these local accelerations can push the flow locally to supersonic speeds, and then once you have supersonic flow, you can have shock waves, and you will see that wave drag in subsonic vehicles arises primarily from this effect, that local pockets of supersonic flow terminating in normal shocks, creating a sudden pressure jump that disrupts the boundary layer, causes flow separation. And as you have seen in that pressure drag due to flow separation, the separated flow often has less pressure than is required to maintain the balance of pressure between aft and fore, and you have a net drag in the direction of the relative wind. So this is what we will take a look at in today's presentation. So let me switch on to the presentation mode. Okay, so this is the slide that I had shown in the last lecture. Just a second. Okay. So if you see this, so this is something that we had shown in the last lecture. So this one is of primary importance in these consideration of wave drag for subsonic vehicles flying close to the sonic state, is that there comes a point where so again look at these images here. So we have low speed vehicle, essentially vehicle flying lesser than the speed of sound. So see Mach M infinity. Okay, so the vehicle as a whole is flying subsonic. You see Mach infinity is 0.3, Mach infinity is 0.5. Here something strange is happening. We are using this special label called MCR. CR will stand for critical, as we will see. We will see why we call it critical. And for this particular airfoil, which is a cross section of the wing that the aircraft is using, the critical Mach number is seen to fall at 0.61. Once again, this is not a constant. It's not a universal constant. Different airfoils will have different critical Mach numbers. For this particular airfoil cross section, the critical Mach number occurs at 0.61, and we will, talk about what is this critical Mach number. So, if you consider when the vehicle is flying at a Mach number of 0.3, there will be a point, say the point A, that reaches where you have the highest velocity and the lowest pressure. If you measure the Mach number at point A for a given m infinity, you will see, for example, when the m infinity is 0.3, this m at A is about 0.435. Once again, this depends on the geometry of the airfoil that you are considering. We are just giving the specific numbers for a particular choice of airfoil. Okay, so this is at the point A, you have the highest Mach number on the top surface, and here pressure is minimum, velocity is maximum, Mach number is also maximum, and it is 0.435. As you crank up m infinity to 0.5, the Mach number at point A increases to 0.772. Furthermore, when you crank it up to 0.61, okay, 0.61, you see that the Mach number at A, which is the point that has the highest Mach number, reaches 1.0. So what happens is this Mach number at which the Mach number at a point on the airfoil surface reaches Mach 1 for the first time, okay? Because you see in this condition, when you cross this 0.61, so here your vehicle is flying at 0.65 Mach. So you understand that although the vehicle is flying subsonic, okay? You remember m infinity is nothing but u infinity divided by a infinity, which essentially means the free stream velocity divided by the speed of sound at in the free stream. So that is m infinity, and when m infinity is less than 1, you understand that u infinity is less than a infinity. That is why it is less than 1. So here your vehicle is flying at a Mach number of 0.65, which is below Mach 1, but it is above Mach critical for this airfoil. You see Mach critical we obtained at 0.61 Mach. So again, the free stream Mach number m infinity for which a location on the wing surface reaches Mach 1 for the first time is known as critical Mach number. In this case, as you cross the critical Mach number, so here we are showing what happens at Mach 0.65, we see that a region of supersonic flow now exists on the on the top surface of the of this airfoil, terminating in a shock wave. The shock wave has, as we discussed briefly, of course, this is something that you will learn in courses on high-speed aerodynamics, the nature of the shock wave, what happens across the shock wave, etc. But we said that the pressure jumps, the static pressure becomes very high, depending on the strength of this wave. So you have a terminating shock wave. The sonic line essentially tells you that at these locations, m is equal to 1, okay, which means if you calculate the u at these locations, divided by the velocity of sound at those locations, you will get m is equal to 1. Now, in the previous lecture, inadvertently, I had put a at this point, but it should not be the case. A is somewhere where the flow Mach number is the highest, and approximately, they kind of fall on each other in these diagrams. So here we have not shown the location of A, okay? So just be careful that this is not A per se. In the previous lecture, by mistake, we had put the point A at the start of this sonic line. So that's not the case. Okay, so the whole idea is at some Mach number, you will reach Mach 1 at some location on the wing for the first time. So that is your critical Mach number, and we will see the significance of this critical Mach number. There is a significant thing that happens at this Mach number. So of course, this is significant enough that even when the vehicle is flying subsonic, you reach sonic condition at a certain point on the wing for the first time. Here, of course, you still reach sonic condition on the wing here. Maybe here it is difficult to say because it's supersonic to subsonic, but at least you see you have the sonic line intersects this at here. So you have sonic condition, but you see there are supersonic states behind it. So 0.65 is no longer the critical Mach number because you have sonic and you have supersonic. So this is not the definition of critical Mach number. Critical Mach number is when a point reaches Mach 1 for the first time, okay? So the flow field overall is subsonic over the wing, but there is one location where the flow has accelerated enough so as to just reach Mach 1. Okay, that is Mach critical. In this case, of course, this is again Mach 1, but there are points on the wing that are now seeing supersonic flow conditions, okay, that have crossed Mach 1. So this is beyond Mach critical. So we will see that what happens is when an aircraft flies at Mach numbers, so we are now focusing on the subsonic range aircrafts. So when you have a subsonic range aircraft flying at, like at a Mach number above Mach critical, you have this formation of, you have this local region of supersonic flow, formation of shock wave, separation region. So this leads to the, a form of pressure drag, you can say, that, that shows up, and we, conventionally call it wave drag. So this is created when subsonic aircrafts are flying at speeds above the critical Mach number, so as to have a pocket of supersonic flow terminating in a shock wave. The shock wave imposes a sharp, unfavorable gradient of pressure on the boundary layer, causes boundary layer separation. And then if you remember our discussion from pressure drag, the separated flow region actually has less pressure recovery. So the pressure from the front part is not properly balanced by the pressure from the rear part, and we have a net, drag force. So if you do not remember our discussion of pressure drag due to flow separation, you can go and take a look at this discussion, because like, of course, these wave structures are dissipative, and power from the engine is getting, wasted in these wave structures. But at the end of the day, this drag force should be obtainable from the pressure distribution on the wing surface. Okay, you go at each point, you find the pressure, you find the force, you resolve it into a resultant force along, components along the relative wind, normal to the relative wind, etc. So at the end of the day, although you have shock waves and stuff, and some argument can be given that, it is wave drag is, because the drag due to the wave is because of a lot of energy from your engine or power plant is being wasted in the waves. But at the end of the day, it is still, surface phenomena. That is, the distribution of these waves and supersonic regions and separated flow, etc., affects the pressure distribution on the wing. And then, if you do not care what is happening in the far field, if you just look at what happens on the wing surface, you should be able to get the drag force on the wing. Okay, so this whole thing that is happening, the supersonic state, the shock wave, the flow separation, all of these influence the distribution of pressure on the wing surface, and you will see that a large increase in drag occurs primarily due to the separation of the boundary layer, which follows the discussion of pressure drag due to flow separation, as we have seen before. In this case, we will further see that the CP, because at high Mach numbers, your CP actually gets accentuated. So then the balance of pressure between the forebody and the aft body becomes even worse, and that is the reason why, the beyond critical Mach number, the wave drag can increase substantially. Now we will see what happens. So at this m infinity greater than Mach critical, you see that if this is a stagnation point and you have this body fitted curvilinear coordinate system S, we see that for these kind of thick airfoils in flying at higher than Mach critical, you have this very large supersonic region extending far away from the surface of the wing. And what happens is we see a relatively strong shock with a very high dPdx or dPds, if you want. And the high adverse pressure gradient imposed on the boundary layer causes, this large flow separation, and that leads to large, so if you again like look at this one, so in this region where you would have had some recovery of pressure here, because the flow separation has happened, you will have a net force in this direction. So this one is part of the way we get drag from these wave generated drag on subsonic vehicles flying close to Mach 1. On the other hand, you will see that there are special airfoils. So this is a thick airfoil. We will see that if in subsequent slides, that when you have a thinner airfoil, you can, you have some advantages. Your critical Mach number actually becomes higher and higher. So thinner your airfoil, you can push your critical Mach number. So for example, here for this thick enough airfoil, your critical Mach number is 0.61. For relatively thinner airfoils, your Mach number can go up to like 0.78, 0.79, etc. So you can increase your critical Mach number by using thinner airfoils. But the problem is these thin airfoils have some problem of structural rigidity. Also, in a lot of these airfoil, in wings you store your fuel. So having thin airfoils is often not the solution. So what we do is this is attributed to Richard Whitcomb from NASA Langley. So he came up with the idea of supercritical airfoil, in which the top surface of the airfoil is kept relatively flat, which almost behaves like the top of a thin airfoil. As a result of that, the local accelerations of the flow is lesser than the local accelerations in this particular airfoil. You have a thick airfoil. If you think of flow with area change, you will see that the flow acceleration, is somehow related to the thickness of your airfoil. Thicker airfoil, more acceleration and decelerations. Thinner airfoil, less acceleration and decelerations. So here in this case of this particular design, you have a, more distributed supersonic flow region that, as you can see, it doesn't extend far away from the wing. Also, the terminating shock is relatively weak. Okay, so what that means is your dpdx, although it is positive, it's adverse, but it is not as strong as you get here. Okay, so it's a much stronger shock that you get here. Whereas for the supercritical airfoil, since the top portion is flat, you have a like more distributed supersonic region. It's not extending all the way away from the surface of the airfoil, and also the supersonic flow ahead of the shock is not of the Mach number of the flow ahead of the shock is considerably lower than what you get here, resulting in a weaker shock. And the weaker shock, although it impinges on the boundary layer, but this first of all, the shock appears further down the airfoil cord section. Okay, here you see it is happening almost at what, 60% or just south of 50% of the cord, whereas here you see it is happening almost at 80% or something like that of the cord. Okay, so you don't have large flow separation region for the supercritical airfoil. Now, because of this, the flattening of the top portion, it can be shown that the camber in this front part of this wing becomes negative, and that reduces the lift at some angle of attack. So what he's done is, to compensate for that loss of lift, the rear portion of the wing actually has a very high angle, or rather positive camber ending in a cusp. And it has been seen that for these kind of wings, you can actually push your critical Mach numbers to 0.8 or even beyond that. Okay, so the supercritical wing section is a way in which you can kind of reduce the effects of this wave drag. You can increase your critical Mach number range, etc. And we will see that there is a practical reason why we want to delay the onset of, we want to delay critical Mach number, because just following critical Mach number, you have something known as the drag divergence Mach number. Okay, so here this M infinity, I have said, is greater than Mach critical, but honestly I should have said M infinity is greater than M drag divergence, which is greater than Mach critical. So we will see that discussion in the next slides. So I will stay away from this for a minute. Let me show you this particular slide. So here, if you plot, so here we are showing CD versus the Mach number, or rather M infinity. Okay, so drag coefficient, and if you remember, drag coefficient is nothing but the drag divided by half rho u square s, where s is some reference area. So you see that for a significant amount of these Mach number range, the CD stays constant at CD naught. Okay, this is because of your skin friction drag and other things. Now, beyond this M critical, what you see is there appears a point known as at some Mach number above the Mach critical, where the CD climbs rapidly. Okay, and this happens close to Mach 1. So I have not mentioned that. So this is the Mach 1 line. So your CD increases suddenly following this Mach drag divergence Mach number, and then it reaches a peak, at the point G here, and then the flow becomes supersonic, or rather your M infinity is supersonic. The vehicle is flying at supersonic speeds on this side of the M is equal to 1 line, and we see that the drag actually falls off. So this one, you can see that the critical Mach number of a wing is an important parameter, because the drag divergence Mach number kind of closely follows the critical Mach number. So if you have somehow reached critical Mach number, it is very likely that local, like small further acceleration of the vehicle can, lead you to this drag divergence Mach number, in which the drag on the vehicle can increase rapidly and significantly. The problem is, when you have this sudden increase of drag, your power plant has to be able to handle that amount of drag. And for quite some time, people had this notion that the drag will increase so much at Mach 1 that one will never be able to cross this barrier. So the idea was, if the drag becomes infinite, for example, so people saw that the drag increases almost uncontrollably beyond this Mach number, which they named as drag divergence Mach number. And for a long time, in the, I think from the 1930s all the way to 1960, early 60, like or late 50s rather, because there is a report in 1959 about these de Havilland, George de Havilland, flying at TH-108 and crashing because of these large drag forces that were generated, close to the speed of sound. So this is known as the drag divergence Mach number, and beyond it, your drag increases significantly, or rather CD increases significantly. And for a long time, as I said, from the 1950 to 1930 to 1959 or 60, there was this notion that it is powered flight may not cross the sound barrier because of the amount of CD that is going to happen at Mach M is equal to 1. And in fact, there were theories that showed that the CD can become infinite when M infinity goes to 1. We will see that there are some flaws in that assumption. You cannot really use that, that form to find CD at Mach 1. Okay, so it is like CD is proportional to 1 by square root of 1 minus M infinity square. So if you put M infinity is equal to 1, CD is becoming infinite. But the problem is, given the assumptions that we have used to derive that CD proportional to 1 by square root of 1 minus M infinity square, that those assumptions are not valid at Mach 1. Okay, so I think people overlook this this assumption, and stalwarts, even in the Volta conference, I think in 1935 or somewhere over there, even they were discussing this infinite CD at M tending towards 1. There was, I think, some oversight of the fact that that form of CD proportional to 1 by square root of 1 minus M infinity square, although of course it goes to infinity if M infinity is equal to 1, but you cannot use that at M infinity is equal to 1. So based on the assumptions that are used in deriving that form. So if you see here, so CD stays constant up to Mach critical. Beyond Mach critical, there is this weird Mach number where the CD increases suddenly, drastically, and the amount of increase is significant, etc. So the problem is, of course, now we have seen that you can, fly through the sound barrier if you have a powerful enough engine, and the whole confusion with, that CD proportional to 1 by square root of 1 minus M infinity square is a wrong thing to use at Mach number M infinity is equal to 1. Okay, so the drag increases a lot near M is equal to 1, as we can see, but it is a finite large number. Okay, it is not that CD becomes infinite. So with a powerful enough engine, you can push through the sound barrier. Now here I have written this area rule body, and the this is your the critical, the supercritical airfoil, where you can actually delay the drag divergence Mach number. Okay, so here your drag divergence Mach number, your Mach critical increases, but your drag divergence Mach number, that kind of the gap between the critical Mach number and the drag divergence Mach number also increases for the supercritical airfoil. So we just had a small discussion about it, just at the beginning of today's class, that for these, because we would like to do two things. One is delay critical Mach number. So instead of say at 0.6, we would like it to happen at 0.8. But on top of that, we would also like the drag divergence Mach number not to lie just behind Mach critical. Okay, we would like the drag divergence Mach number also to get a little, the distance between Mach critical and Mach drag divergence should also be large enough for, having a decent margin of safety. So in supercritical airfoils, we have that situation where you can actually push your drag divergence Mach number, to higher values, and the gap between your, the critical Mach number and the drag divergence Mach number can also be increased. You see that here, your delay of the drag divergence Mach number actually happens, and beyond that, of course, you have the rise in CD, as you see in other airfoils as well. But nonetheless, these pushing of the drag divergence Mach number to higher Mach number ranges is of significant use. On the other hand, your drag divergence Mach number still happens at the same point, but the amount of drag does not become as high as this one in case of area rule bodies. So now this is also another contribution from Richard Whitcomb, where he showed that if you make your vehicle as a whole in such a way that the cross-sectional areas, if you take area cross-section between these two, you get the areas at these 2 points. So if somehow you design your vehicle such that your cross-sectional area, as you move from the nose of the vehicle to the tail of the vehicle, doesn't change a lot, then it's called an area ruled body. And there, even though you have increase in drag beyond these drag divergence Mach number, the increase is not so significant. Okay, so these are two methods credited to Richard Whitcomb of NASA Langley that have helped us navigate the the flight near the sonic sound barrier, or like not sonic sound barrier, like sound barrier, or rather m is equal to 1 condition. So once again, as you see here in the inset, we show the flow field around a point F, on the rising curve of this of the CD. So how the flow state looks at a point or flow Mach number that is above the drag divergence Mach number, where your CD is increasing rapidly and almost unboundedly. As you can see, you have these portions of supersonic flow. Your m infinity is still below Mach 1, as you can see. This Mach 1 is actually somewhere here. So this is your Mach 1. So your m infinity is still less than Mach 1, but it is now greater than Mach critical and is actually greater than Mach drag divergence as well. So you see that we get this extended area of supersonic flow terminating in a shock wave. We have adverse pressure gradient causing flow separation. On the bottom portion as well, you can have pockets of supersonic flow terminating in shock waves that impose adverse pressure gradient, causing flow separation from the bottom surface of the airfoil as well. So this is just a like a experimentally determined flow field of what happens on the airfoil in terms of the shock wave and flow separation, etc. at a point above the drag divergence Mach number. You can see that these large, these strong shock waves formed on the top and bottom create this flow separation, and create the lack of balance between forces on the wing from the front and rear, creating this large drag component. We call it wave drag, because the primary source is the shock waves impinging on the boundary layer, causing large flow separation. So now, if we go back to this slide, so here we talk about this important concept where your CP. Now remember that in the previous slide we were talking about CD versus Mach number. In the previous slide, we were talking about CD versus Mach number. Here we are talking about CP versus Mach number. So what happens is it can be shown that CP is actually proportional to square root of 1 minus, proportional to 1 by square root of 1 minus m infinity square. And this is based on, the potential, velocity potential formulation for a irrotational flow field. But, when we talk about when we bring in this velocity potential formulation for irrotational flow, we apply it for the incompressible flow field. I think a lot of you will be familiar with that, or we will go into the discussion of that when we talk about lift. So we will talk about the velocity potential formulation for irrotational incompressible flow. We will talk about the unit flow fields that can be combined to generate a complicated flow field, flow over a cylinder, flow over a rotating cylinder, etc. However, in this particular diagram, what you see is based on the velocity potential formulation for irrotational but compressible flow field. Okay, because remember, wave drag, your shock waves are a compressible flow phenomena. Okay, so here we are flying at large enough Mach numbers where shock waves are happening. So in this case, the velocity potential formulation based on which we get this plot is applied to irrotational compressible flow fields. Okay, and then there is something called the small perturbation approach or linearization. You will hear these words. Small perturbation essentially means that if you have a slender body like the wing or a fuselage is a slender body at small angles of attack, etc., the velocities can be broken down into mean velocity and some perturbations, and those perturbations are small. Based on these kind of assumptions, it can be shown that Cp is proportional to 1 divided by square root of 1 minus m infinity square for the subsonic part. Okay, this is your vehicle is flying subsonic, and then you are so you find Cp, and then you can see that Cp has a dependence of Mach number like this. Okay, Cp at a given point has a dependence of Mach number like this. So we will again see this thing on the left hand side plot. But before we get into that, I want to draw your attention to this thing that on the supersonic leg, Cp actually follows a similar rule, but here instead of 1 minus m infinity square, it is m infinity square minus 1. So of course you understand that Cp has to do with pressure distribution. Cp is P minus P infinity by half rho u square. So if Cp follows this distribution, many things that follow from pressure distribution would also follow a similar trend. In fact, it can be shown that Cl, Cm, etc. follow the similar trend. And in terms of the wave drag, if you have flow separation, etc., it is really the disbalance of pressure. So it is influenced by the Cp distribution in the fore part and the aft part of the wing. So there also these 1 minus m square influence shows up in a similar fashion, creating that large rise in CD as we reach Mach 1. So here we are looking at Cp versus Mach number, showing a large rise in Cp as you approach Mach 1. And if you remember, this image is similar to that CD versus m infinity. So we essentially said that, okay, this is m critical. Then at some point behind m critical, we have this thing called the m drag divergence. So you can say mdd, m drag divergence, beyond which your drag CD increases unboundedly, and you can, this curve is actually reminiscent of, or rather, has some analogy with that CD rise of the CD curve, and you can see that at some point it again, become. So this is at Mach 1, and then it falls. So this is supersonic. So you see that there is some analogy in the trends of this Cp and the CD curve, and partly because that Cp influences the CD in a similar fashion. So here we say variation of linearized. So that linearized what is important. We are applying actually the velocity potential formulation to irrotational compressible flow fields. And then we are using small perturbation approach, or we are assuming small perturbations. Essentially, slender flow over slender bodies at small angles of attack can be considered as a good candidate for this linearization, and thereby we get the Cp distributions as you see in this image. Okay, so CP increases as you approach Mach 1 from both sides, from subsonic to Mach 1 or supersonic, reduce it to Mach 1. You see CP increases significantly, and the flavor of this CP change is reflected in the CD distribution that we saw in the previous slide. In experiments, actually, it has been seen that your CP, so what you do is you measure CP at a point A at a low enough Mach number. So remember that beyond 0.3, the compressibility effects come in. Okay, so if you want to measure CP at a low enough Mach number, so you need to go to something less than 0.3, favorably less than 0.2 as well. So this is perhaps something that you get. Now, if you measure the CP at this point at other Mach numbers, you see that it follows a trend like this. We have the Prandtl-Glort curve fit, which essentially gives you a way in which you can obtain this CP by just finding CP at. So what this thing is saying, so this is the Prandtl-Glort correlation. What this thing is saying is to find CP at a location A at a given Mach number, all you have to do is find CP at A at a very low Mach number. Okay, so less than 0.2 or as low as you can. Then you use this correction. So you divide it by the square root of 1 minus m infinity square, the m infinity at which you're interested to find the CP at. Okay, so these are the experimental data of CP at a point A. And Prandtl and Glort, they showed that, so this is the Prandtl-Glort curve, which is obtained by finding CP at this location and then by dividing it by square root of 1 minus m infinity square. So suppose I know the value of CP around this point. Okay, say I know this value, and say then at 0.7, all I have to do is take this value, divide it by square root of 1 minus 0.7 square. So I'll get this value here. So this is the Prandtl-Glort curve. Rather, you can think of it as a model. That is, if you do not want to, if you don't have the facility to measure CP at those high Mach numbers, all you can do is measure CP at a low enough Mach number and then use this correction. Okay. So CP0A is calculated at A under low speed conditions. As you can see, I have said Mach number less than 0.3, but again, I think less than 0.2 might be a safer bet. Okay, so that is the Prandtl-Glort correlation. There are some more advanced and I think a little bit complicated looking fits, like the Karman-Cien fit and the Lightons fit. I think the Karman-Cien is the one that is widely used in aircraft manufacturing centers. But the Prandtl-Glort, because it follows the theory as well, is something that is of interest. So as you can see, your CP actually is influenced by Mach number. Okay, so one crucial problem in these in the consideration of wave drag in these vehicles is to figure out your Mach critical, because you remember that just behind Mach critical your Mach drag divergence is sitting, and beyond that Mach drag divergence your CD shoots abruptly. So you do not want to get into that portion, right? Like where you cross, so where your vehicle is flying above Mach drag divergence. So it is important then to know what is your Mach critical, because your Mach drag divergence, beyond which you really do not want to play at. We know that the Mach drag divergence comes behind the Mach critical. So if you have a way in which you can find the Mach critical, then it's of some use. That is, if you do not cross your Mach critical, or at least you know the margin that you have between Mach critical and Mach drag divergence, then you at least have some safety in terms of when you are going to hit that very large rise in CD. Once again, that rise in CD, as you see here, it is not infinite. Okay, if you see, your CD being influenced by this 1 by square root of 1 minus m infinity square could have become infinite at m infinity is equal to 1. But that assumption, this whole, the based on which we say that the dependence on this 1 minus m infinity square happens. The assumptions actually do not hold at m is equal to 1. So you cannot say that just put m infinity is equal to 1 and you get infinite Cp, and if you integrate it, if there is flow separation, then there is a very high Cp on the front, unbalanced pressure in the rear portion of the wing. So of course, in that case, the drag can be infinite, but it doesn't happen that way because this theory is based on the assumption that it's not Mach 1. Okay, now that we have seen the way in which Cp varies with m infinity, we will try to find a way in which we can estimate the Mach critical. Okay, so here you see that. So think of the previous slide. So this one is that Cp versus Mach number plot. Okay, remember how to get it? You can just find. So Cp is given by P minus P infinity by half rho infinity U infinity square. So what you do is you find Cp, say at a point where that maximum acceleration, or rather where the maximum velocity or maximum Mach number occurs. Okay, so point A is the point where the maximum velocity or maximum Mach number, hence the minimum pressure, etc. occurs. So at that point A, I am going to find my because see that point A will eventually, because that's the point where you are having the highest Mach number. So when you arrive at Mach 1, your point A is going to reach Mach 1, before any other point reaches Mach 1. So first what you do is you find Cp0. So Cp at point A at a low enough Mach number. Then you correct it using the Prandtl-Gloert or some kind of correlation. So this is then, so you can use something like this. So first find Cp at a low enough Mach number, Cp at A at a low enough Mach number. Then by using this correction of Mach with Mach number, you find the Cp distribution. Now here you see that for the thick airfoil, so this is for the thick airfoil, this is the curve. So this is for the thick airfoil, okay. We said that for the thin airfoil is a way to push the critical Mach number further. As you will see that, for example, here you see Mach critical thick, Mach critical for the thin. Okay. So thin wing cross sections, Mach critical is much higher than that for the thick wings cross section. Thick wing cross sections Mach critical. Of course, we have not talked about this other line, so we have to find. So there are these two lines. One is the Cp at that point where that maximum Mach number occurs. So you find the Cp at that point, correct it for Mach number, you get this plot. Similarly, you can think of the thin one. So for the thin wing, so for the thin airfoil, here your Cp at that point will be, less than the Cp. So the point A here and the point A there can be different. So let me just call it A prime. Or as long as you keep in mind that every airfoil will have that location where as you expose it to a flow field, its local Mach number at that point will be higher than the Mach number at any other points, and that point will reach Mach 1 before any other point reaches Mach 1. But then beyond that, what happens is something else. At least in the subsonic portion, till any point on the wing surface reaches Mach 1, it is really that point A. So it depends on the geometry of the airfoil where your A is located. But once you find that point A, you find the Cp0 at point A, and as we have said that you find it at a low enough Mach number, then you use a correction like this to find the Cp distribution. So this tells you that what will be Cp at this. So for the blue, okay, this is the blue curve. So this is Cp0 for the thin. And then you correct it with that, this using this correction for other Mach numbers, and you see that this plot becomes something like this. Okay. Now, if this is something that we have not done in our coursework right now, but this is something that is there in compressible flow theory, And you see that although we have talked about that Bernoulli's theorem should be used only for incompressible flow fields, etc. We have not talked properly about what is a compressible flow field, but we said that above 0.3, above Mach 0.3, changes in velocity creates substantial changes in pressure, which in turn can create substantial changes in density. So changes in pressure creating substantial changes in density essentially falls under the category of compressible flow fields. And that happens, the change in density is significant when the flow Mach numbers are beyond 0.3. So in that case, because remember now when we are discussing critical Mach number, etc., we are no longer talking about the low speed Mach number range, right? So we are talking about Mach numbers above 0.3. So Mach numbers 0.65, as you have seen in one case. For the thin, you might even have Mach critical going up to 0.7, 0.75. So here your compressibility effects are dominating. Of course, you don't have shock waves in subsonic flow fields, but we said that you can have local supersonic flow fields in these cases. But nonetheless, we have to now look at this equation that comes from compressible flow theory. That is, so we do not want to get into the details of this, but at this point, I just want to explain how we get this curve. Because once you get this curve, so let me just change the color of this curve to green. Okay, so I'm now talking about, so how to get this red and blue curve, you know. The point A on these and the point A on this do not need to be the same, but that point with respect to that particular airfoil is nothing but a point where the flow reaches the maximum Mach number or the maximum velocity or the minimum pressure, etc., for a given m infinity. And as such, as you crank up your m infinity reaches m1, so the point A or A prime reaches point Mach 1 before any other point reaches subsonic or supersonic states. Now I'm going to talk about how to get this curve, because once you get this curve, then you can get the critical Mach numbers from the intersection. So once you get the green curve, then you can get your we will look at the intersection between green and the red. To get the critical for the thin, we will look at the intersection between the green and the blue. So the question is, how do we get that green curve? So if you look at this one, P naught by PA is given by 1 plus gamma minus 1 by 2 ma square to the power gamma by gamma minus 1. Okay, so this is nothing but a connection between P naught, which is known as the stagnation pressure. You can think of it as a total pressure. That is, if you have a field, you bring the flow to rest isentropically. Now we have not talked about this thing, but nonetheless, it's an introductory course. It's useful to hear some of these terms so that by the time you go to the real course and see these things, you will at least remember that we had talked about this thing. So here, P naught is stagnation pressure and PA is the static pressure at the location A. MA is the Mach number at the location A. Okay, and gamma is nothing but Cp by Cv, the gas or the medium in question. So this equation gives you a connection stagnation pressure and pressure at A and Mach number at A. Okay. Similarly, this expression gives you a connection between stagnation pressure and the free stream static pressure. So to get, you have to use the free stream Mach number. Similarly here, to get the static pressure at A, you have to use the Mach number at A. To get the static pressure at infinity or free stream, you need to get the free stream Mach number. Okay, so you see these two things are connected. Pen color, let me just switch to red. So once again, P naught is something known as stagnation pressure. Okay, is the static pressure at the location A. MA is the Mach number at the location A. Gamma is Cp by V for the gas under consideration. In most cases, we will be dealing with air. Here again, you see P naught is the same. So now we are interested in finding P infinity. So we have to change the subscript from A here to infinity. So we have to use the free stream Mach number to get the free stream static pressure given P naught. Similarly, given P naught here, we have to use the local Mach number m at A to get the P at A. Okay. So once you get these things, the assumption is your P naught stays the same. So unless you have a shock wave through which the flow goes, you have your your P naught doesn't change. And so far as we are talking about flow fields at the critical Mach number and below, we have a sonic condition at location A, but we still do not have the supersonic or the shock waves. Okay, we are not going into beyond Mach critical, approaching Mach critical. So we can still assume that P naught is not changing, because if you have a shock wave, then your P naught can change. So this P becomes a bit tricky. You have to justify that point. But just trying to find the critical Mach number, and you say, well, we don't have shock waves in the system at up to this point. Then you can say that your P naught here and P naught here are the same. So then if you divide these by each other, you get P at A, so static pressure at A, divided by static pressure in the free stream, can be given by these relationship, where m infinity is free stream Mach number and ma is Mach number at point A. And so here we have, and this thing follows just from this expression. Now let us look at what is Cp at the location A. So you see Cp is defined as P minus P infinity by Q infinity, which is half rho U infinity square. And that you can just use this form to get to this form. And Q infinity, which is half rho infinity U infinity square, can be written like this, which eventually becomes this thing. So here this thing is nothing but the velocity of sound square. Okay, gamma P by rho. So A is actually square root of gamma P by rho. We have not shown these derivations yet, but again, we will derive these things once we are done with something known as the Reynolds transport theorem. Okay, so here we are bringing A square. So V square by A square becomes this. So V infinity square by A infinity square. So this is infinity because see, we are using P infinity and rho infinity. So the ratio becomes M infinity square. Essentially, then we have a definition of Q infinity in terms of P infinity and M infinity. So here now what we are doing is we are just plugging in this formula Cp. Then we are replacing Q infinity using this formula here. Okay, so you have P infinity divided by the expression for Q infinity from here. So gamma by 2 P infinity M infinity square, and then in the bracket this PA by P infinity, right? So this is the ratio of static pressure at location A divided by static pressure at free stream. So you just follows from this relation. So you write this. So Cp at A can be written to be this form. So here you see that at the location A we have MA, whereas at free stream we have M infinity. Now if I want to find Cp at A, assuming that A has reached sonic condition. Okay, so this location A or location A on the location A at the thin airfoil, location A at the thick airfoil. So what I'm saying is I'm changing M infinity, and at some point my MA has become 1. So that is the definition state. Okay, so the M infinity for which MA becomes 1 for the first time. Okay, so that is the critical Mach number. So then I can say Cp critical. We don't have to say Cp critical at A because that point A is a unique point. It is the point on the airfoil where flow becomes sonic for the first time. Okay, so when we say CPCR, the assumption of that unique point is there. So we don't write that CPA critical. So we just say Cp critical then is nothing but the same expression here, but instead of MA, we will plug MA is equal to 1. So this one follows from this expression with MA set to 1. Okay, so you have reached sonic conditions. So then Cp critical is given by this expression. Interestingly, this M infinity is nothing but the critical Mach number. right? Because it is that m infinity where ma has become 1. Okay, so then we can write this form, that is Cp critical is a function of m infinity, but like implicitly that m infinity is actually m critical. So then you can plot this Cp critical versus Mach number plot, and wherever you have the intersection, you can see that you have reached that Mach ma is equal to 1. So then the corresponding Mach number becomes the critical Mach number for that particular airfoil. Okay, and also see that here your thick airfoil, because the flow, if you think of the area velocity kind of thing, you will see that flow comes to a stagnation stop at the leading edge. I mean, depending on the orientation, though, the location of that stagnation point can vary. Um, but the flow reaches stagnation, which is a peak velocity at point A. So what is happening here is you see that for the thick airfoil, because your turning is quite large, your Cp values actually become quite large as well, because the flow is turning, or the flow is going through a large area change. On the other hand, for thin airfoils, you see that your Cp is actually on the lower side. So P minus P infinity. So P is not deviating too much from P infinity. So that's the idea. In fact, sometimes, as I said in the previous slide, that have this large M critical, it is advisable to use thin airfoils, and that this slide kind of describes why so. So thick airfoils have low critical Mach numbers. Thin airfoils have larger critical Mach numbers. So if your vehicle is flying at high subsonic speeds, you might be tempted to use a thin airfoil, because you have a higher Mach critical, which means your Mach drag divergence that is waiting just behind Mach critical is also pushed behind. If you can push your Mach critical to higher values, then your drag divergence Mach number is also pushed to higher values. But the problem is, as I said, the structural rigidity of the thin wing or thin airfoil cross section is a little tricky, and also sometimes if we use the wing for storing fuel, a thin airfoil doesn't serve our purpose too well. So for that, we use this supercritical airfoil. So it's still a thick airfoil. It's almost like the airfoils that we have seen for low-speed vehicles. But here, what happens is, while the top surface is flat, like in a thin airfoil, the bottom surface is thick enough, and it has this very large positive camber at the trailing 30% region. Okay, if you think of the full chord as 100%, then the first 60 to 70%, you actually have. I mean, I cannot say the first 70%, but in the initial portion of this region, you actually have negative camber for the supercritical airfoils. But nonetheless, these supercritical airfoils allow you to move the critical Mach number to higher Mach numbers, and also it lets you delay the drag divergence Mach number with respect to the critical Mach number. So it gives you a lot of advantage in vehicles that are flying in the transonic range. A lot of modern day aircrafts actually use this particular airfoil design. So having said that, and we have talked about area rule, we have talked about supercritical airfoil. In the next class, I will quickly talk about ways. So you saw today that we use thin airfoils, or we can use supercritical airfoils to, fly at these high subsonic, near sonic conditions. But there is this idea of sweep back or swept back wings, which are also employed to mitigate the effects of high Mach number flight. This is something that we will discuss in our next class. So with that, I will end today's presentation. Thank you, and we will continue in the next lecture.